Well, hello everyone, and welcome to part 4 of string graphs. This is the fourth of 4 in the series, and whether you have been here for all 4 of them, or whether this is your first one or anything in between, it's going to be important for us to take a look at what's gone on before and what we're going to be doing today. Today, you'll see that we have differences tables being the focus of our activities, where we're going to link the coordinates of the intersection points. My name is Roger Wander. I will be leading you through today's webinar and taking a look at some aspects, first of all, of the program thus far, and then more importantly, taking a look at the special kinds of activities that Task 4 asks us to do. In Activity 1, we were concentrating on this concept of string graphs, which was nothing more than taking selected points along the x-axis and the y-axis, so the coordinate axes, and connecting those selected points in such a manner that a curved type of shape seemed to appear, but we were doing these with very definitely straight lines. It's a nice little optical illusion that we said had a nice link to some architectural concepts that have been seen right throughout the world. Possibly some of you have seen them in real life. And certainly in the first of the webinars, you were taken through some photos of various places, including a lovely bridge in Jerusalem that was designed incorporating some of these activities. So in the first activity, the guidelines, if you will, the lines where the connecting points were found, were the coordinate axes. In the second part, we looked at stitching not between the coordinate axes, but between a couple of lines of opposite gradient. In the actual Part 2 task on the TI website, those two guiding lines were y equals negative x and y equals positive x. You have connecting lines such as the one that's now on your screen between negative 10, 10 and 1, 1. And we revised some of those ideas of finding the gradient using the 2 points, and then finding the equation of the line based on other levels of algebra, with eventually leading to the familiar y equals mx plus c. One of those 10 lines that was developed in the task is there on the screen for you. You notice the presence of fractions, and for those of you who are new to this series, the importance of using the exact values, which in this case are fractions, as opposed to decimal approximations, is extremely important if we want to develop the algebra that precisely describes the relationships. And that's one of the main goals of this entire series, is to see how algebra and function notation can be used to gather together lots of information about a visual and numerical pattern that we see. The beauty of this one, of course, was that if you take a look at the curve that emerges and do enough lines with that, you do get this very beautiful and visually appealing symmetric curve. And that was done when the guidelines were y equals negative x and y equals positive x. In the next activity, in task 3, we were concentrating on, well, let's find where the points of intersection, but not any old points of intersection, not the ones, say, down here or over here, but rather where consecutive lines were intersecting. And we used the simultaneous equations ideas that you have developed in your own classrooms with your teachers, and we saw how Nspire could be used to find the coordinates of the points of intersection. As the points of intersection between line 1 and line 2, between line 2 and line 3, etc. So the idea of between consecutive lines was a really important concept. And we used the subscript T to denote the number of the line. We also then started to refer to T being used for the number of the pair of lines, so that line 1 and line 2 were the first pair, line 2 and line 3 were the second pair. There was a lot going on in the third part of string graphs, and simultaneous equation work was a main feature of that. Now in the fourth task, we go back to our original, and this is a pretty important concept, that we're going back to the curve that we found back in the first part, where the guiding lines were once again the coordinate axes, but the same kind of thing applied. And we are trying in this last of the four parts to describe the pattern that's formed by those points of intersection that seem to be in a curved shape. Is there some sort of algebra that can connect the x and y coordinates of each one of those points? Well, we're going to use the graphs here to look at how that's done as part of this webinar. It should be kept in mind, however, that we have a noticeable increase in the challenge of what's being done in this task. I believe the activity sheet is 6 pages long, and there is no beg pardons for how complicated it's getting. It's probably a good idea to remind you at this stage, being in, we're recording this now in the third term, many of you in year 10 are making some pretty serious subject selection decisions about 2021. And particularly for those of you who are moving towards looking at doing year 11 specialist mathematics, the use today of some of the maths that doesn't normally appear in year 10 is going to be talked about. Your teachers might decide to support you with some units on that this term, or possibly in the terms to come. But just a warning that there is some challenging mathematics coming up, but we'll be guiding you through that in this tutorial. Well, let's take a look at some features of the Part 4 worksheet, which is now up on the Texas Instruments website. String graphs Part 4, aimed for year 10, but take a look at the two aims, and particularly that we are focusing on the rule connecting consecutive points of intersection. Now, the word rule is sometimes referred to as an equation, but the rule is the algebraic connection that we're looking at to connect consecutive points of intersection. And because these coordinates for the example that I showed you before up here, those coordinates of points of intersection are fairly complicated. I think nearly all of them are fractional, and they're not the usual 1/4, 1/8 fractions, but some pretty challenging ones. We have to have some sort of a strategy that we use for that, and that's using something called difference tables. So the focus of the maths that we do today in this webinar is going to be on what a difference table is, how it's used, and then how we use something called matrices to do our calculations for us. They're also, possibly surprising to you, will be a little bit of trial and error. It's not really surprising to those of us who are dealing in mathematics quite a bit, because trial and error is one of the ways that we solve problems, that we see patterns. So we embrace that rather than being able to say, let's go straight to the answer. Let's do some experimenting and be comfortable with the fact that that's a very valid way to learn. Okay, well, I'm taking this screenshot from page 1 of the activity sheet for task 4. And while this is not the one that we are actually going to be examining, because it's printed for you, and I am hoping that you have in front of you somewhere on screen, or maybe a printed out version of the task sheet, because it would be easier for you to follow all of what we're doing here. That task sheet is on the website. This is from page 1, and it's question 1, and it's just taking a look at the concept of a difference table. And so we're going to just take a look at the structure of this one, but we will be actually, in our work today with Nspire, we'll be taking a look at a different one. But it's a similar kind of situation. Okay, the first thing to notice is that the table has 5 rows, and the top 2 rows are dealing with the x and the y coordinates from the relationship. So there's how we locate. The first point is 1, 6. Then we have 2, 11. Then we have the ordered pair 3, 18, etc. I believe there are 9 or 10 of those points placed there on that difference table. I'm just showing you the left side of it to highlight that. So those points are the relationship. We're trying to see what's the pattern. How are those y coordinates being generated from all of the x coordinates? Now, one way to do that is to start to take a look at how the y coordinates change as you go from the first y coordinate 6 to the next y coordinate 11. Well, that's a bump up of 5. So 5 represents the difference. You notice this symbol, it's a triangle with a 1. That triangle is a symbol that's used a lot in mathematics, and in higher mathematics, it's used for the word change. So the first change, and in your quadratics work, you've used that possibly for the discriminant. It is actually the Greek letter delta, which in the Greek language serves the same purpose. It makes the d sound. So here it's standing for differences. That's why it's used in this table for the first differences. And this row, the third row here, is talking about the differences between the points that are above it and just to the left. So 11 minus 6 is 5. 18 minus 11 is 7. 27 minus 18 is 9. So clearly, while the x coordinates are going up by 1, there's a constant change in the x coordinates, the y coordinate differences, they seem to be growing apart. First 5, then 7, then 9. And when this kind of thing happens, we know straight away that those points do not lie on the same line. If you choose to plot them just on a piece of graph paper or using Nspire if you wanted to, you would see that they do not line up in a straight line. Well, what else is happening here? What's another feature of the differences table? We have something called the second differences. You see the symbol delta 2. And they are the differences of the differences, if you will. 7 minus 5 is 2. 9 minus 7 is also 2. Now, this turns out to be a really important thing because we have taken the second differences and it's there. It's in this fourth row that we found commonality in the second differences. Not the same differences. 5 is different to 7, is different to 9, but the second differences are all the same. And that tells us a great deal of information about how the coordinates here might be related. Well, let's keep going here now. Another main feature of a differences table is what the author of the string graphs activity has referred to as the leading edge. That's 6, which is the first y coordinate, the 5, which is the first difference, the 2, which is the second difference, and actually the 0, which is the third difference. If we kept going on this, you would populate that whole table. Those 4 numbers are extremely important, and they form what's called the leading edge of the difference table. And in another burst of new material for you that you've never seen before, we're going to put them into something called a matrix. And a matrix is something that for most of you might recall some movies from a few years ago. But a matrix in mathematics is just a rectangular array of numbers. Very, very useful for making lots of computations at once. And today we're looking at matrices that are formed this way. This is called a column matrix, where we have 4 rows. The rows run horizontally, but we have 1 column. Okay, and Nspire can help us with those as well. So 6520 is what you're aiming for on the activity sheet. The activity sheet also has a couple of screenshots from Nspire that show you where we are getting these values. And you notice that we have a menu here that looks maybe different from anything you've seen before, and that's because it comes from a notes page. So there's a third new application. It's maybe not new for some of you, but for others of you, the notes page is something that you've never used on Nspire. So I'll be guiding you through that and showing you how we actually do all of these calculations. Now, our challenge today is to take a look at the another pattern of points, which are, as you can remember from before, this time it's 1, 1, 2, 7, 3, 15, 4, 25, etc. And we're going to try to find out what rule links up those coordinates. Well, the first thing we have to do is populate the differences table. So the first differences, I hope you can understand why that would be 6, 7 minus 1, 8, 15 minus 7, etc. And once again, they're going up by 2s. The second differences show that clearly. The second differences are all the same. Now, our hint for this is that if the second differences become constant, and the fact that these are second differences and the number is 2 is a coincidence. It's not always going to be the number 2, but it's very important that you recognize the second differences. That tells us we probably have a quadratic relationship. Quadratic relationship is one that has x squared in it. So x and y are going to be connected by something that involves x squared. The third differences are zeros, and that becomes important only in the fact that 1, 6, 2, 0 will be the leading edge, and it will form the numbers of the leading edge matrix. Remember that, write that down. 1, 6, 2, 0 in a column will be the bleeding edge matrix that we're going to be trying to achieve when we do our Nspire calculations. So we now go on to Nspire to see how that's actually done. And this will support some of the things that you are asked to do on that Activity 4 worksheet. So I'm going to open up my file. And this file, by the way, will be available to you on the TI website. Right now, it's just got some information here. I am on a notes page, and it doesn't look much like a notes page. I suppose it doesn't look like the calculator page. It doesn't have any special background. But when we press menu, you can see that you've got quite different commands, subroutines that you could engage with and in if you wished to. So I'll just escape from that and go back. And I'm referring here, excuse me, I'm referring here to other places on the Part 4 worksheet where you have some background of some of the algebra that's here that there's just too much for us to go through in the short time of the webinar. But it's reminding you that one of the things that you did in questions 4 through 6 on that activity sheet was look at the constant, the linear, and the quadratic basic functions which had leading edge numbers that caused us to be able to denote certain matrices. So what I'm going to do is start by putting my cursor here at the end. I press enter to squeeze a line in here so you can see how this is working different than the comments did on the calculator page. And what we're going to do here is insert a maths box. Now in Nspire term, it's called a math box. And the easiest way to get to that is to press Control M. Whoop, and I've got to back that up. Hold down Control and press M, and you can see a little box with a dotted line around it. What the math box is something that enables us to write down algebra and symbolism that we would normally save for the calculator page. It's very, very handy. So it's been acting like a word processor at the start, and now all of a sudden we're using some of the features of calculation. Now we're going to be doing some assigning. And this assigning is shown on the task page. So we're going to assign the name P0. So I press P, the numeral 0. It's really important to have that rather than the letter O. So P0, and that will get assigned. Remember from previous work, that's Control Math Template. And we want to assign to that a matrix. Well, where do we find the matrices? Well, you notice on that button that's now red, because that was the last button I pressed, it's got that template. So without pressing Control, if you press that template button again, we have a whole variety of possible templates. You see, we could put in a fraction if we wanted to, or you can put in some calculus, or you can put degrees and minutes, etc., square roots, a whole lot of different ones. Well, we're going to choose this one, which has the square brackets and then the 3 rows of 3 dots. We choose that, and that's the matrix button, and we are invited now to create a matrix. Now, you remember from a few pages ago on our PowerPoint that we were looking at a very tall, skinny matrix. It was called a column matrix. That means that we had 4 entries in it. There are 4 rows, so we need to bump the default from 3 up to 4. And the number of columns has to be reduced to 1. So that will set up what's called a 4x1 rows by columns, a 4x1 matrix. I click OK, and you see we've got now the cursor is in the top box ready for us to enter these values. And from you will have to reference the worksheet there to see why the leading edge has the numbers 1, 0, 0, 0. I'm just going to enter them in here now, 1, and then use the down arrow key, 0, 0, 0. And I'm going to now take my cursor one space to the right. I'm still in the math box, and I'm going to press enter, which just confirms the fact that we have assigned the matrix 1, 0, 0, 0 to our symbol P0. That means a 0-degree polynomial, which means a polynomial where the only index that x is raised to is the power of 0. We're going to do the same thing for x1. I put my cursor at the end. I press enter. I want to put in a math box, so Control M. I'm this time going to assign P1. So I do that in the manner that I did before. Control Math Template, then press the Math Template again. Once again, I have to specify that I want 4 rows, I want 1 column. But the numbers for a linear polynomial, which is what P1 is standing for, where x is to the power of 1, the basic polynomial, and you'll see these difference tables when you look back at your sheet. So there's a lot of stopping of the video probably that you're going to be wanting to do just to catch up with this, because I'm linking lots of different ideas. We're going to put in 1, 1, 0, 0. I take the cursor one place to the right, and I press enter, so that tells me that P1 is locked in. Going further down the screen up here, we have for the quadratic polynomial, y equals x squared, the leading edge was 1, 3, 2, 0. So again, a math box, Control M. We're going to define P2. Or we're going to assign it. It's very good to get the wording correctly on here. And we press Control Math Template once again to put that symbol up. And once again, we want a matrix, which will be a 4 by 1. And we're going to put in the numbers 1, 3, 2, 0. Go to the right, press enter. And those are going to be the building blocks that we use. Remember, at any time we can go back up here and see what we've got so far, and we can even go back up to the top. But we've got our 3 matrices assigned, P0, P1, P2, and you'll be very happy to know we don't need to access those anymore. We can use the symbols. Now, here's an important part. Using these 3 matrices, we're going to find the quadratic, and I'm giving you that hint. And it's a quadratic because the differences were the same at level 2, at the second differences. That links the points 1, 1, 2, 7, 3, 15, etc. There were several of them. And we want to do our calculations in such a way that the leading edge matrix that we found, and that was back on the PowerPoint, is 1, 6, 2, 0. That's what we're aiming for. And what do we mean by we're aiming for that? Well, we are aiming for us to be able to take experimental quadratics. And I'm starting with 2x squared minus 2x plus 3. And this is where for some of you, the uncomfortable guessing game begins, because if you think about it, you could have all sorts of different combinations of polynomial expressions where you have coefficient for the x squared term, a coefficient for the linear term, a coefficient for the constant term. And we're going to be trying out that polynomial as our first one, and then gradually working our way towards being able to come up with a solution of 1, 6, 2, 0. When we have then we have discovered the link between X and Y. Now, your teacher might explain how that all works. We don't have time for that here in this webinar, but just follow along, use a little bit of trust that we know what we're doing, and hopefully we'll be able to see that. So to try that particular polynomial, right in this same line, I'm going to insert a math box. I don't need to have it start at the beginning. Inserting the math box. And I'm going to write the coefficient of the x squared is 2, but I'm going to have put in my variable p2, because that's the quadratic part. So that's sort of like 2x squared, if you will, if you want to call it that. And then minus 2p1, and then plus 3p0. Now each of those matrices is going to be multiplied by, the first matrix is going to be multiplied by 2, the p1 matrix multiplied by -2, the p0 matrix is multiplied by 3. And when I press enter, I'm hoping to get 1620, but I don't. And this is like you see on the activity sheet. You've got to go through a whole series of changes. I'm going to go up here and copy, just for the sake of doing this really quickly, I'm going to copy this part because I'm only going to change one of these. And say, well, suppose instead of 2x squared, we have 1x squared. It's really good on this experimenting to just do one bit at a time. Okay, suppose it's 1x squared minus 2x plus 3. Now notice up here we got 3, 4, 4. They weren't the numbers here at all. The only number that was the same was the 0, and that's going to happen in these. But we're trying to get these numbers to match up. Let's press enter and see what happens. So we've got that in the math box, and when I'm in the math box and press, whoops. That's right, I've got to put in another math box. So I once again go Control M, and I've got to put in the calculation 1p2. Minus 2p1 plus 3. Let's see, plus 3p0. Okay, well, let's see how we go there. When I press enter, well, it's quite different, but the good bit is that we now have, can you see the 2 down there? That's the same as the 2 that was in the third position in that column matrix. So we've made progress. We've made progress on that. Now, because this is only a half-hour video, I'm going to go right to what I have found out through experimentation is the actual answer here, just to show you how it does work. And I'm going to try the try didn't need to be in the math box. Control M. Y equals x squared plus 3x minus 3. So insert another math box, Control M. And to try that one, you notice the coefficient of x squared is 1, so we're going to calculate 1p2. The coefficient of the x term is 3, so plus 3p1. And then finally we have -3. So -3 P0. When I press enter, I get the 1620. That's what we were aiming for. There's the 1620. Now, in actual fact, when you're doing this, it may take you a long time, depending on how lucky you get with your questions or with your sample quadratics. But keep on, persist, and then you're really working like a mathematician. Now, since y equals x squared plus 3x minus 3 is the value, just to show you, this is just to finally show you that this actually does work, because what does work mean? It means that it describes the points that were in that original table that we had on the PowerPoint slide. I've copied that equation, y equals x squared plus 3x minus 3. I'm going to open up a calculator page, which is press the house key here and go to a calculator page. That's one way to do it. And I'm going to Control V, which is our paste command. And what we're going to do is this mass substitution of all the x values from 1 to 10. And to do that most efficiently, if I press Control equals and use the vertical line, which means such that or given that, then I'm going to say, well, let's sub in not one x value, not at a time. That can be very slow. Let's put in a whole bunch of them. X equals, and to put in a bunch of values, you might remember that we did this a couple of webinars ago by accessing the curly brackets, which are control closed brackets here. And into that list, we're going to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When I press enter, we should get the y values that tag along with each of those, and there they are. You'll notice the point 1, 1, the point 2, 7, the point 3, 15. They are exactly the same as what we had in our original differences table. And so you have got a little bit of an idea of how Nspire can use the matrices that we have developed, P1, P2, and P0. And if you needed to deal with a cubic, you would use P3 as well. I'm only using those first three. And use those to try to build up a matrix that looks like the leading edge matrix. Once we've done that, we've got our quadratic, we've got our relationship, and we can then, on the calculator page, we can verify that it's worked. Okay, well, we've come to the end of our time with this work. I will show you that, as promised, it does get pretty complicated at the end of this task, and you are using two different differences tables. By the time you get to questions 13 and 15, you're finding an expression linking x with the equation pair t, and then you're doing it later with the value of y with the equation pair t. And I think the presence of fractions rather than whole numbers there give you an indication of just how careful you are going to have to be. But care will be rewarded with some really interesting mathematics. And that's the reason that we're doing this in the first place, to challenge you to get into this work and to appreciate the fact that all these areas of mathematics are linked and they can be producing some pretty interesting results. So thanks so much for watching. Be sure to check out other student videos on our website. Take care.